Okay, now we're going to talk about a particular kind of pressure, which is going to be called static pressure. And so when we talked about energy in lesson number 6, we said that there were two kinds of mechanical energy: potential energy and kinetic energy. Now we'll talk about the kinetic energy part later. So for right now, let's just talk about what was potential energy. So potential energy was energy of position. And there were many different kinds of potential energy, but we talked about gravitational potential energy, and so we said that E sub P was going to be equal to M, G, and then H. So H would be the height that you would raise something. G would be gravity, 9.8 meters per second squared, and then M would be the mass of the object. And so the higher up you lift it, the more potential energy you're going to have. Well, we could have added one additional term to this, and so we could have said that the potential energy that you have depends on the amount of potential energy that you start with, and then plus the added potential energy of when you lift it up to that height. But normally what we did was we made this part equal to 0. And we said that this was going to be the potential energy when the height was 0. So if h is 0, 0 times anything is 0. And so we could just let this thing be 0. Now what we want to do is to take this thing and then write it in terms of pressure. So when it is a solid, normally we talk about the energy of the solid. But when it's a fluid, either a gas or a liquid, it's normally better to talk about its pressure. And so the way that we can relate this is through the concept of work. And so work, W, was going to be equal to a force and then multiplied by a distance r. And now what we can do is substitute, instead of the letter F in there, we can substitute our definition of pressure. So since pressure, P, is equal to force divided by area, then that means that if we take the A over to this side, that the force on an object is going to be its pressure multiplied by area. So now we can take this and put it down here, and so now we're going to have a pressure multiplied by an area multiplied by a distance r. And notice that if you've got a box that has a, let's put it over here, so let's say that you've got a box here, we could say that the area A of the box multiplied by the length of the box, r, is going to be the volume of the box. So therefore we could say that the work is going to be equal to pressure times volume. So the energy in a fluid system, whether it's a gas or a liquid, is going to be the pressure that's being applied to it times the volume of the fluid that's being moved. Okay, now we could take that equation and then plug it into this equation here. So then what you're going to end up with is that the pressure, so this is the pressure that you end with, is equal to the pressure that you begin with, okay, plus, all right, now we're going to need to do a little bit of work on this term over here. So we're going to be dividing it by the volume of the thing, and then mass divided by volume is density. So this part here, mass divided by volume, is going to be the density of it. And then you still have the G and the H. So it's going to be density, G, and then H. So our final formula is that the pressure that you feel is going to be equal to the pressure you start with plus the density of the fluid, gravity, 9.8 meters per second squared, and then how deep you are under the water. And so so if this fluid is water, then we say that the P0, the initial pressure, is going to be the atmospheric pressure that's pushing down on the water. All right, so here is a sample question. What is the total pressure felt by a diver in water at a depth of 30 meters? So we're going to write down what we're given and then what we're looking for. And then we know that you can look it up on the internet and find out what is atmospheric pressure in terms of newtons per square meter. And then we'll plug our numbers into the formula, and that will tell us the pressure at that particular depth. All right, let's take a break, and when we come back, we're going to start talking about things that are moving.